Download this code from codegive.com, link in the description below. OK, let's dive deep into binary comparison for patch diffing using tools like bindiff. This is a complex topic, but I'll break it down into manageable parts with explanations and code examples, where applicable, as bindiff's core functionality is visual. Understanding binary patching and diffing. What is binary patching? Binary patching is the process of modifying an executable file, a binary, directly, usually by replacing or inserting bytes. This is often done to fix bugs, add features, or apply security updates without recompiling the entire program from source code. Think of it as a surgical strike on the binary. What is binary diffing, or comparison? Binary diffing is the process of comparing two binary files, usually two versions of the same program, to identify the differences between them. These differences can range from small changes in functions to entire functions being added or removed. Why is binary diffing important? Reverse engineering. Understanding how a program has changed between versions is vital for reverse engineers to analyze bug fixes, security vulnerabilities, or new features. Vulnerability analysis. Identifying where vulnerabilities were patched helps security researchers understand the nature of those vulnerabilities and how they might be exploited in older versions. Malware analysis. Comparing a malware sample to a known clean version can reveal what malicious code has been added. Patch creation. While manual, binary diffing can help understand the exact bytes that need to be changed when creating patches. Code reuse detection. Identifying reused code across different versions of a program. Security audits. Verifying that a patch does what it is supposed to do and doesn't introduce new vulnerabilities. Challenges of binary diffing. No source code. Often, you don't have the original source code. You're working with compiled machine code, which is much harder to understand directly. Compiler variations. Even if the source code is the same, different compilers or compiler settings can produce different binary code. Address changes. Relocations and address space layout randomization, ASLR, can shift code around in memory, making direct byte-by-byte comparisons unreliable. Obfuscation. Malware authors deliberately try to make binaries harder to analyze, including making diffing more difficult. Code generation changes. Minor source code changes can lead to significant differences in the generated machine code. Dynamic linking. Binaries often rely on external libraries, DLLs, shared objects. Changes in these libraries can affect the binary. 2. Tools for binary diffing. Bindiff, the primary focus. Bindiff is a powerful commercial, with a free trial, tool that is considered the industry standard for binary diffing. It provides a visual interface for comparing the control flow graphs, CFGs, of functions in two binaries and identifying similarities and differences. It handles things like function reordering, address space changes, and instruction set variations, to some extent. It's excellent for understanding high-level changes in code logic. Developed by Google. IDA Pro with the Diaphora plugin. IDA Pro is a widely used disassembler and debugger. The Diaphora plugin is a strong open-source alternative to bindiff for function similarity analysis and binary diffing. It can handle larger binaries well. RadArray2. RadArray2 is an open-source reverse engineering framework with powerful diffing capabilities. It's more command-line oriented than bindiff but highly scriptable and flexible. ZDiff/comp, basic byte-level diffing. These are basic command-line tools for comparing files. They are useful for quickly identifying identical regions but less helpful for understanding code logic changes. Other tools. Ghidra*, a free and open source reverse engineering suite from the NSA. It includes diffing capabilities, though not as mature as bindiff or diaphora. TurboDiff*, a chimerical offering that is specifically designed for binary differencing. 3. A detailed bindiff tutorial. Let's walk through a practical example using bindiff. Since I can't directly interact with the GUI in this text environment, I'll describe the steps and interpret the results as if you were using bindiff. Scenario*, imagine you have two versions of a simple program called myprogram.exe. myprogram_v1.exe, the original version. myprogram_v2.exe, a patched version with a bug fix. Steps*. 1. Installation and setup*. Download and install bindiff. The trial version is sufficient for learning. Ensure that you have IDA Pro installed, as bindiff integrates with IDA Pro for disassembly. Bindiff uses IDA Pro's disassembler engine. 2. Loading binaries into bindiff*. Launch bindiff. Go to File-New. Select myprogram_v1.exe as the primary binary and myprogram_v2.exe as the secondary binary. Click OK. Bindiff will launch IDA Pro in the background to disassemble the files. This may take some time, depending on the size of the binaries. Bindiff will then perform its analysis. 3. The bindiff interface*. Bindiff's interface is divided into several key areas. Function list*. This lists all the functions found in both binaries, along with a similarity score. The higher the score, the more similar the function. Control flow graph, CFG, view*. This shows the graphical representation of the control flow within a selected function in each binary. Nodes represent basic blocks of code, and edges represent the flow of control. Disassembly view*. This shows the disassembled code for a selected basic block in each binary. Similarity histogram*. A graphical representation of the overall similarity between the two binaries. Address map*. An overview of the address layout of the loaded binaries. 4. Analyzing the results*. Sort by similarity*. In the function list, sort the functions by the similarity column, click the column header. This will group similar functions together. Start with functions that have low similarity scores. Examine dissimilar functions*. Select a function with a low similarity score, example below 50%. Bindiff will display the CFG for that function in both binaries side by side. Color coding*. Bindiff uses color coding to indicate differences. Green*. Identical code. Yellow*. Similar code with minor differences. Red*. Significantly different or missing code. Gray*. Unmatched code, present in one binary but not the other. Follow the red*. Focus on the red-colored blocks in the CFG. These are the areas where the code has changed. Disassembly view*. Click on a red block to see the disassembled code for that block in both binaries. This will allow you to see the exact instructions that have changed. For example, you might see that a conditional jump, Jane, has been flipped, or that a calculation has been modified. Unmatched functions*. Look for functions that are only present in one binary. These might represent new features or code that has been removed. Bindiff will indicate if a function is primary only, in the first binary, or secondary only, In the second binary. Manual matching sometimes, bindiff may not automatically match functions correctly. You can manually match functions by selecting them in the function list and using the match option, usually in the right-click context menu. This is helpful when functions have been renamed or significantly restructured but still perform a similar task. You will need to manually find the addresses in the disassembly and map them correctly. 5. Interpreting the differences bug fixes A common change is an updated error check, which might involve a change in conditional jumps or modified calculations. Look for changes in comparison instructions and jumps. Feature additions new functions or code blocks may be present only in the updated binary. Security patches patches often involve input validation, sanitization, or the removal of vulnerable code. Look for changes in code that handles user input or network communication. Example, a simple bug fix scenario. Let's say myprogram_v1.exe had a buffer overflow vulnerability. In myprogram_v2.exe, this was fixed. 1. Bindiff analysis after loading the binaries, you notice that a function called process_input has a low similarity score. 2. CFG view The CFG view shows that a section of code in process_input is colored red in myprogram_v2.exe. 3. Disassembly view The disassembly view reveals that in myprogram_v1.exe, the code looked like this. And in myprogram_v2.exe, it looks like this. 4. Interpretation The myprogram_v2.exe version now has a size check before copying the user input to the buffer. If the input is larger than 256 bytes, it jumps to an error handler, overflow_error. This prevents the buffer overflow. The code that was added in v2 is a comparison statement CMPEX 256 and a conditional jump JGA overflow_error. 4. Practical tips and best practices. Start with familiar binaries. Begin by diffing simple, well understood binaries to get comfortable with bindiff's interface and color coding. Focus on the CFGs. The CFG view is the most valuable part of bindiff. It allows you to quickly identify the regions of code that have changed. Learn assembly. A basic understanding of assembly language is essential for interpreting the disassembled code. Use debugging tools. Combine bindiff with a debugger, like IDA Pro or x64dbg, to step through the code and understand how the changes affect program behavior. Loading both binaries into the debugger can help you step through the same code sections side by side. Address space awareness. Pay attention to address space randomization, ASLR. Bindiff can often handle ASLR, but sometimes you may need to manually adjust address offsets. Library dependencies. If the binaries use external libraries, make sure you have the correct versions of those libraries available. Changes in the libraries can affect the diffing results. Compiler optimization. Different compiler optimization levels can produce very different code. Try to use binaries compiled with similar optimization settings. Handling large binaries. Diffing very large binaries can be slow. Try to narrow down the areas of interest before performing the full diff. IDA Pro integration. Bindiff's integration with IDA Pro is crucial. Learn how to use IDA Pro's features, such as cross-references and function renaming, to improve your analysis. Scripting. Advanced bindiff has a scripting API that allows you to automate certain tasks. This can be useful for large-scale analysis. Asterisk comments and annotations. Asterisk use bindiff's commenting features to add notes and explanations to the diff results. This will help you keep track of your findings and share them with others. V-code example, illustrative, not bindiff specific. Since bindiff is a visual tool, I can't give you direct bindiff code. However, here's a very simplified Python example that shows the basic idea of byte-level diffing, but remember, this is far less sophisticated than bindiff. Important notes about the code example asterisk. Asterisk rudimentary asterisk. This is a very basic example. It doesn't handle address space randomization, function reordering, or instruction set differences. It's purely a byte-by-byte comparison. Asterisk not for complex analysis asterisk. This kind of byte-level diffing is only useful for very minor changes or to verify that small patches have been applied correctly. Asterisk noisy output asterisk diffing executables. This way will typically generate a lot of output because of slight variations in timestamps, compiler-generated data, etc. 6. Advanced topics, brief overview. Asterisk instruction set architecture, ISA, awareness asterisk. Some diffing tools can handle different ISAs, example comparing x86 code to ARM code. Asterisk fuzzy hashing asterisk techniques like imphash and steep generate hashes that are sensitive to code structure but tolerant to minor variations. These hashes can be used to identify similar functions even if the exact byte sequences differ. Asterisk symbol matching asterisk. If the binaries contain debugging symbols, PDB files on Windows, dwarf on Linux, diffing tools can use these symbols to match functions and variables more accurately. Asterisk control flow graph normalization asterisk. Normalizing the CFG can improve matching by removing address dependencies and focusing on the logical structure of the code. 7. Conclusion. Binary diffing is a challenging but incredibly valuable skill for reverse engineers, security researchers, and anyone who needs to understand how software changes. Bindiff is a powerful tool that can significantly simplify the process, but it's important to have a solid understanding of the underlying concepts and to combine it with other tools and techniques. Practice with different binaries and scenarios to develop your skills.